in time. Section 1.6, we talk about, I'll put down my protein bar, parent functions. We need to get the basics of them so that we can transform them in section 1.7. So linear, basics. What is, coming into this class, what was the most preferred form of a line, the equation of a line that you guys would use, almost always? Slope, of just the line, slope-intercept form. Yeah, y equals mx plus b. So the first line. That was the old preferred method. What's the new preferred method? Point slope, which is y? And where do you plug in? In slope-intercept, you just plug in a slope and a y-intercept, which is great if you have a slope and a y-intercept. What's nice about point slope? You plug in a slope and 1 point. What point? Who cares? Any point. Any point that's on the line. Does not have to be the intercept, does not have to be special. That's, that's why this guy is preferred. I'm choking on my protein bar. Struggle. Okay. But I want you guys to think about a normal line. Ooh, that's a bad word. Normal has a mathematical meaning coming from Latin to do with perpendicular. Regular. Thank you. Regular line. Okay, just think of a line in your head. Like there's an XY axis, think of a line. Any line. Not just one of those. Just a line. Okay. Question. What would the domain be of said random line in your head? How left does your line go? Yeah, it keeps going left and left and left and left and left? Like in the line, however it looks. Okay, how right does it go? Most lines have a domain of all real numbers, which interval notation we've been trying to master, negative infinity to infinity. Think about your line. How low does it go? Most lines have a range of all real numbers, or the y variable is within negative infinity to infinity. Because most of your lines were slanted. True? Did anybody use a straight up and down line? Ooh. Did anybody use a horizontal line? Now, those of you that used a straight up and down or a horizontal line, you should not have answered these. One of them is right, but one of them is wrong. Let's use really quickly an example. Down here, we'll do vertical line right here and horizontal line. Really quickly review from when we talked about it before. Vertical lines, they're tick marks on the x-axis, if you were to think about it that way. It's just a little tick mark that's been extended. It's an x equals constant. Horizontal lines, they're little tick marks on the y-axis. So they're little y equals a constant. I'm going to say y equals d just to have it be another name. Help me out. What's the slope of a vertical line? Good. It is infinite. But technically, how do we answer it at this level? Zero is this one. He's the one that you can ski. He would just be really, really boring. His slope is flat. 0. This one, it is infinite, and I love that you remembered that. But what would you be if you skied it? You'd be dead. What's the word I used in class? Undefined. There it is. Undefined is the typical way of describing it. But you're right. It is infinite slope. You're right. Steeper, 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 steeper. You just keep on going to infinity. It is undefined slope. But here's my question for these two lines. What would the domain be of a vertical line? Just, no. It doesn't go left or right. It only goes down and up. The domain is one x value, and it's used over and over and over and over and over and over, but it's only one x. This would be the point 1, 2, 3, 4, 4, 0, 4, 1, 4, 2, 4, 3, 4, 10, 4, 100, 4, negative 1, 4.7654. Anyway, the x is always the same. Now, what's the range? All real numbers. The range would be negative infinity to infinity. That's why I said you're half right. One of these will be right, but the other one will be restricted. What's going on in the horizontal line? What's the domain? All real numbers, forever left, forever right. But what's the range? just the constant y equals d. Because you're going to have the point 1, what did I actually put? 4-ish, 5-ish? 1, 5, 2, 5, 5, 5, negative 3, 5, negative 0.333333335. The x's can go all the way through negative infinity to infinity, but the y's, that's a d, I apologize, not a 2. The y's will always be the same number. Anyway, there's only 2 times where the domain and range of a line will be anything other than all real numbers. Coming back up here, if m is positive, m being rise over run, you're going to have a sloped up line, right? If m is negative, you're going to have a sloped down line. And by slope, we already talked about slope. It was in section, what, 1.5, 1.4? Rise over run. So remember, as you're doing slope, if you are graphing a line, just to do the rise and the run. If the rise is positive, go up and over. If the rise is negative, go down and over. Okay, with that, let me zoom in at the very, very bottom. These are just 2, constant and identity were 2 very different names. That's awkward. Somehow they got squished together. We'll just move them all the way down there. Oh, and now they're absolutely gone. Oh, that's why. Okay. There's the constant function and the identity function. Let me zoom in. The constant function we actually kind of talk about right here. He's also known as a horizontal line, so we kind of, used him twice. But the constant function, the function value is constant, y equals d. That's not what I wanted. But he does have a name, technically. And then the identity function is y equals x. And there technically is the reciprocal of the identity. He's kind of special, too, y equals negative x. You can go the other direction, but it's all right. Y equals x, this one's super basic in the sense that it has the point 0, 0, 1, 1, yeah, exactly, 2, 2, negative 1, negative 1, et cetera, et cetera, et cetera. Okay, he's going to be important when we get to section 1.9, but we're not there yet. That's linear. Let's talk about quadratic. Now, this is not the section where we go super crazy into completing the square and into like crazy, crazy factoring and into all this algebraic playing with quadratics and finding their vertices, and we're just doing the basics. So, basic quadratic is y equals x squared, okay? Basic parabola hits the origin at 0, 0, has the points 1, 1, negative 1, 1. We could keep on going. 2 squared is 4, so 2, 4. Negative 2 squared is 4. You might not know why I'm putting the points, but I'm just letting you know it's super helpful. Why is this so much higher than the other? I have no clue, and I apologize. There we go. That's better. One thing about a quadratic is that you have what's called the vertex, which can either, in general, be a minimum or a maximum. Some people would call it like a peak, like a mountain peak, even though it's a hill peak, but that's okay. A peak, like a top, maximum, or a valley at the very, very bottom, that'd be a minimum. Totally depends on the concavity of the parabola. If you guys didn't already know the shape of a quadratic, we would call it a parabola. And a parabola, let me put in parentheses actually, has one type of concavity. That might sound a little weird until we get to the cubic function, then maybe it'll make a little bit more sense. But a parabola has one type of concavity. Let me show you what I mean by that. A vertex will be a minimum if the parabola is what we would call concave up. Concave up. Silly, I think of concave up like a cup in the sense of, or you can just think of the parabola as going up. But either way, concave up like a cup, I can hold water in that. I can't hold water and concave down like a frown. And the concavities, that's down, sorry. The concavities are pretty basic when they look like this. They really are. They're pretty basic. It's like, okay, it's a smile, it's a frown, whatever, got it. Concave up, concave down. It's not like lenses with concave, convex if you're trying to think of like science. We're not going there. That did not even help. But the struggle is if the entire, like in other types of functions, you'll see actually today a couple examples. In other functions, it might not have the entire concavity, like the entire cup. It might just have half of the branch, and we still say it's concave up. Might have the other half, still say it's concave up. Might just have half concave down, down. So I'm showing you the full thing. Every parabola only has one type of concavity. This one, concave up. That's the normal one. But depending on the concavity, we either have minimums or we have maximums. And then you guys know, I mean, this can flip over. This can like shift around. It can stretch with all those transformations. So when we need to, we'll talk about how if you did have, let's see, what different types of forms. Now these are transformed equations, so be careful. You won't really be seeing them in this section. You won't even really be dealing with them much until we have like a special section just on quadratics. But this is the one everyone's used to. We've already used this one for factoring, for zeros, for x-intercepts. You could do the quadratic formula to this guy. He's super basic, and he's not bad. The only problem is there's a better one with lines. And the better one is y equals a times x minus h squared plus k. Because this one, like the standard form of a circle equation, I won't say it because some people are taking a test, but the standard form of a circle equation had an h and a k in it too. Remember how we were able to pull out a certain special point and do some different things? This one, the hk, is called, or is, the vertex. And there is a formula that you could memorize. Kind of looks like the quadratic formula, but a lot easier. There is a formula how to get h out of this guy, but this form would just give it to you straight away. Oh, hey, there's h, there's k, da da da, that's the vertex. Swoop, there it is. Kind of, if you get a few points. But anyway, those equations, and for our purposes, like point slope, this one's really going to be one of the more helpful forms eventually, but we'll get there. This isn't the section where we go into tons of detail on that. Last thing I want to cover is domain and range. So let's look at this really basic guy. So 4y equals x squared. Just the super basic one. Hello, eraser. Okay, what's the domain for y equals x squared? Look at that parabola. How left will he go? Good, you're just going to keep on expanding, right? And you can keep on going to x's, and you can square any negative x or any positive x. But range answers the question, how low to how high, right? How low does he go?
0.
He's stuck by his vertex. So he only goes down to the minimum, which is 0, and how high does he go? Good. He's just going to keep on going up, 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 up. Okay. Basics, quadratic, we got him. Who's the next guy? Cubic. X cubed. Does anybody know his shape right away?
Like this?
Kind of. Yeah, it's kind of like that. He's over there. Where's the cubic guy? That's a line. That's the y equals x. That's the identity function. That's negative x. Here it is. You kind of have to have like a swoopy, and then you have to have like a swoopy. Yep, just like that. So, swoop, swoop. Cubics. 2 concavities. Do you guys see both the concavities?
Yeah.
Doesn't have a full concave down or concave up, but that's okay. I see a frown and I see a smile. The question is, do you? We would call this portion of it concave down. We would call this portion of it concave up. So cubic function has 2 different concavities, and here's something spiffy. We'll talk more in chapter 2. Any even degreed polynomial, x squared, x to the 4th, x to the 6th, x to the 8th, will always only have one concavity. unless it starts being like twisted in between and having like weird W's and rises, etc. But a basic x squared, x to the fourth, x to the sixth will look like a parabola, just be skinnier. And any basic odd one will be like this, but will be skinnier also. That doesn't mean there can't be funny things that happen with higher degrees, but that's the basic one.
See, it means like if it's cubic, if it's like even, it only has one positive value. Like if it's even power, it only has positive values, but if it's odd, it can have negative.
It has something to do with that, yes. But depending on what else is there, like with the pluses and minuses, you can have negatives and positives in. Yeah. But in general, you're right, Joe. Okay, so we have, what were we talking about? Two concavities. We already kind of labeled them. There is a special point for this guy, for cubics, called a point of inflection, or an inflection point. We'll talk more about him when we need to. In general, he's just the separator. He kind of separates the domain. One side is one concavity, the other side is another concavity. Point of inflection occur between the concavities. That's kind of a good description for a point of inflection. What else do we have? There isn't like really pretty special equations for cubics like there was for the quadratics or the linear functions. He could just be called a polynomial, but we're not going to go into that. I don't think there's really anything else I want to talk about besides domain and range. So just for this guy, just for f of x equals x cubed. How left, how right? Because I could keep on plugging in negative x's and they'd all have an answer. Similar with linear. Remember, except for the special ones. And range, I see how low, how high he go. Do you agree with Joe? Well, wait. The question was, do you agree with Joe? Yeah. It's going to keep going down, 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 up, 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 yeah. Negative infinity to infinity. Okay. And as Joe already mentioned, part of the reason for these two separate branches, one going down, one going up, is because if you plug a cubed number into, sorry, not a cube number, a positive number in cube it, it will stay positive, hence why this one's going up. A negative number in cube it, what happens? Stays negative, so that's why it's going down. Okay, square root function, otherwise known as the radical function. Sorry, maybe I should have used square root instead. Wrong name. Radical functions more general. You could have a squared root, cubed root, fourth root. So we're just keeping it basic, just the square root. That's okay. F of x equals the square root of x. He doesn't exactly have a special name for that point. It's not a vertex specifically. It's not a center. It's not, it could be an intercept, but it doesn't have to be. It can be shifted all over the place. But I will say that it has just one concavity again. But it never really completes that entire, like it doesn't act like a parabola. It won't end up going down. The square root function just keeps on going up and up and up and up and up. Slowly, to be honest. Having the points of 0, 0, 1, 1. What would be the next nice point? Well, 2 square root 2. Mrs. Leon could give us a decimal equivalent, but 3 and square root 3, 4 and, I like 4. There we go. 4 and 2. I totally just realized I did not put reference points. Oh, wrong way, wrong way. I did not put reference points on my cubic, did I? Cubic has 0, 0, 1, 1, -1, -1. So similar to the identity function, like the line, except so different. Because what would the next nice point be? 2, 8. Yeah, it would be like way up here. Not that you have to do 2, 8, and 2, -8, but just the idea you plug in a positive, excuse me, get a positive, plug in a negative, get a negative, etc. Just to give you some reference points for the cubic. Sorry, here's the square root function back again. One concavity, we talked about his key points that you can use when we start transforming them in another section. Let's go ahead and talk about, yeah, let's do it here. What should we be thinking as soon as we see a square root and we're thinking don't? Can't be positive, can be positive, can't be 0. Can't be negative underneath, right? So don't we have to think of our domain problem? And our domain problem says take the right-hand and set it greater than or equal to 0. That's our quick little reminder, right? That was our domain problem clue. We have to watch out for radicands, denominators, and what was that third one that we didn't actually use in the section, but I said it was coming? Logarithms, good. So this one has a radical. Radicand has to be greater than 0. What does that mean for interval notation? How left does it go? How right? Good. Now here's what's weird. How low does it go? This one, yeah. How high? So domain and range are both restricted. That's a little for this guy. Neither one is all real numbers. It's kind of just randomly cut off, but it's not random at all. I'm just going to do, and this is, I know it's silly, but for some of you, I think you really need to see it. The square root of 0 is 0. That's totally allowed, totally legal. You're allowed to plug 0 into a square root. Just a few people are like, undefined. No, it's 0 squared is 0. It's okay. Square root of 0 is 0. We're allowed to do 0. That's why we have the or equal to. And it just disappeared kind of. That's why we have the or equal to. It's allowed to be 0. It's just not, the argument's not allowed to be negative. And that's why we have this nice little point right here. Because this is the marker of the beginning of the x's that are allowed. So square root function always starts in a point, always swoops from there, only having one concavity, but it's always restricted domain and range. Okay. Reciprocal function. Can you guys see them? It's f of x equals 1 over x. The basic reciprocal function. How many concavities? Good. What's this side? Yeah. It doesn't have to have, remember? Just does it look like a frown? Yeah, it looks like a frown. Okay, concave down. So what's this side? Got it. What's the point in the middle? What? So what is? What kind of asymptote? Good. I have a vertical asymptote in between the concavities. No point of inflection. Because no point can exist. But Matthew is right. We totally have a horizontal asymptote also. So we have a horizontal asymptote. We have a vertical asymptote. Horizontal asymptote would technically be y equals 0. Vertical asymptote would be x equals 0. That's what's splitting up the concavities. The book, just quick heads up, will almost never draw asymptotes. Because they're giving you like a electronic representation of a graph. Asymptotes aren't there, so they don't get graphed. Doesn't mean that you didn't do it in Algebra 1 and Algebra 2, but anyway, just quick heads up. So what's the domain? All real numbers except where the denominator is 0, right? Domain problem. So therefore, if we were to do this in interval notation, this is where it gets a little bit rough. X can't be 0, I get that. But does it make sense, check it, that this is how you would write it? U is a spiffy mathematical symbol for union, which means or. Union, which means or. I think it's a symbol from geometry, like when you guys did like this implies, contrapositives, converse. What are the other ones? I don't know. If P, then Q, things like that. I don't know. Something in geometry. Long time ago. Study geometry for the SAT. Okay, so sweet guy though, CPK. But if you were to write an interval notation, does it make sense that the 0 is not included?
Yes.
It's like everything left up to 0, but not including 0. Everything right, but not 0 either, right? Everything right, sorry, but to the left, not including 0. So that's the way to write it in interval notation. I know it's kind of easy. X isn't 0, or all real numbers where X is not 0, but that's technically the snazzy way of writing it. How would we write the range? Same with domain, because who's not allowed, or what does it not cross? 0. So yeah, it'd be the exact same. If you guys need to, you can go ahead and do a quick little like note to yourself. Remember, technically has to do with union, technically symbolizes the word or. We're going to see it when we do probability next semester, but there you go. I think that's all I want to say. There's no point in the middle because there are asymptotes. Yeah, I think we're good. Who's next? Ooh, piecewise functions. Okay, hold on. We've seen piecewise functions. What were we doing where we saw piecewise functions this year? Graphing calculator handbook. Perfect. Wait a minute. Graphing calculator handbook. Wouldn't it be nice to have it to use in case you want to graph any piecewise functions tonight? The correct answer is yes. Okay, so if you're awake and not too focused on taking notes. Theoretically, if my TA was amazing, which she is, except she's not in this class. There we go. I think these are in rows, so find yours and pass back. Uh-oh. Oh, Nehemiah's gone today. Didn't take roll yet. There we go. Here you go, Lauren. Find yours, pass back. Find yours, pass back. Find yours, pass back. Find yours, pass. Uh-oh. Two of these got stuck together. There you go. These grades have been on RenWeb for a while, I believe. I just didn't really have a reason to pass these back earlier, I don't think. Are you getting your what? Oh, I am so sorry. Graded ones are right there, but the TA didn't finish. She's going to finish next period. If on your way out, if you see your notebook at the front, grab it. It's already graded. The grade's inputted in my grade book and in the notebook itself. And if yours isn't there, pop in anytime during lunch, during grade 7, after school. It'll be done. Is that cool? Thank you so much for bringing that up. There you go. Nehemiah. Okay, pass back. For some reason, I thought it was BC's notebooks, but it was yours. Hopefully one of them is yours. Okay, last one. Uh-oh. Matthew, do you have a random extra paper? Can you pass it up for me? I think Emma, yours is over there. Let me go get it. Lauren, here you go. Wesley, here you go. So there you go. Chris, there you go. Thank you, thank you. And Emma, here you go. Cool. Why did I hand back the Precalc graphing calculator handbook? Isn't it back here? Ooh. Right there, yeah? Okay, piecewise function. Remember, he's the guy who's defined in pieces. So you have like a piece 1. What's piece 1? I don't know, linear, quadratic, square root, polynomial, something, 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 for some sort of like, I don't know, x less than c. Totally different function for x greater than or equal to c and maybe less than some other guy d. And then you might have some other hi, that's imaginary, j. X greater than or equal to You could have all sorts of different pieces. You could have 2 or 3 or 4 or 10. A really cool Precalc Algebra 2 technically, but could be Precalc project, is to use this nice graphing software called Desmos. And you have to make a picture entirely of piecewise functions. That's kind of cool. It's technically a great Algebra 2 project. But, oh, I don't know. Maybe. Oh. It's a cool project. Artistic people get to have fun, but then it's really frustrating trying to get functions that fit the like shapes that you want to make for the, anyway. Some people just like do a clown with like a hat and eyes. And, anyway. But then you have to do like a parabola for like a smile and then like a, anyway. Coming back. Step function, there are 2 really special, I'll just do y equals. There are 2 really special piecewise functions. You're going to see them tonight in homework. These 2 are actually the reason why this homework isn't due tomorrow by 7 a.m. I have pretty high confidence that most of you could probably figure out how to do these 2 functions in the book and basically be able to be done with this homework tonight, which is why tomorrow we might do a little bit more on 1.6, but we're going to start on 1.7 tomorrow also, just to give us plenty of time on 1.7. Transformations, they're messy, there's a lot going on. So my advice would be to work as much as you can on 1.6 homework tonight, maybe even finishing it. I think you could, because you've seen this guy before. That guy you could just kind of, the one problem guess on and see how you do. All right, cool kids, I'll see you tomorrow. Thank you, thank you. These are the graded ones, yeah. Anything up here, come grab. Whoops, anything in the back? Wait until lunchtime. Or 7th period.